So I've been experimenting with this concept of time delay of arrival of signals. Uh, Pat WB2 CMF has been helping me out from his home, hosting one of the two tiles that we're using in this experiment. The other's at my home. So we have Port Jefferson Station and Farmingville are the two locations. Uh, One of the tests is trying to get a bearing on the National Weather Station, National Weather Service radio transmitter, Eastern Long Island. And as you might know, the system requires a reference signal to sync up the two ties, the two pies, the two tiles. So we're using one right now from a digital TV station. So I'm going to command the two tiles now to simultaneously listen to that reference signal, take a snippet from the weather station, and listen to the reference signal one more time and capture that data. So now that the tiles have captured the data, I've got to get that data back into my laptop here so that we can do the comparison. So I'll send the command now to both tiles to send their data back to me. And the one on the left has done it already. It's on my local area network, so it's faster. And Pat's, of course, is coming through the internet. And he's almost finished. There you go. So now that we have the data in my computer, one of the things I can do is analyze it. We have its IQ data, and I can play that data and listen to the audio, any audio modulation, using a tool called New Radio, which I will demonstrate for you now. So here is GNU Radio, and it's a really neat program for building up software-defined radios. This particular block diagram, there's the source file, which is what the tile captured. It's going to access that. It's going to de-interleave, which means it's going to take the I's and the Q's and separate them, because the data that came out of the tile, the first byte is in-phase data, and the next byte is quadrature data, and they alternate back and forth. So it de-interleaves them and splits the stream, so to speak, and sends the I's in one branch and the Q's in another. And since it's positive data, and we want plus or minus data, we take subtract 127 from each byte, because the bytes in there are from 0 to 255. So now we'll have minus 27 to 128. So that works out well. Do some other processing here. Well, we're multiplying the constants so that we can now take them and here we convert them to a float, and here it goes from a float to a complex number, which can be handled first by this low-pass filter, and then I have a little squelch here, and I have a narrowband FM receiver module. So it does, it does the FFT, it does whatever it has to do. And I also have a sync here, which will show us some graphical representations. And if I scroll down, you'll see two more boxes. This one here is virtually a volume control. It accomplishes that just by increasing the values of the audio stream coming out of the FM receiver by a simple multiply. So everything is digital. It's magic. Then you have the audio sync, which is sampling. Right now it's 16 kilohertz, and it will present audio to the speakers. So we'll listen to the tile in Port Jeff Station, its sample. You'll hear some digital first, sounds like noise. You hear a snippet from the weather station, and then finally the last part of the block repeats monitoring the digital station as a recheck. So here we go. All right, a little bit difficult to hear. Sometimes it's clearer, but it sounded like he was saying partly cloudy. So if we go to the capture from Pat's tile in Farmingville, we'd hope to hear that same phrase, and that would tell us that we were in synchronization. So I'm going to play that one now. Right, it's difficult to hear, but he said partly. I didn't hear the cloudy part, so that's due to probably a little bit of a few milliseconds off, but close enough. And depending on how I set the gains, etc., sometimes that's a lot clearer. Normally it's a lot clearer, but we'll make do with that for now. And so that's a check that I can do. And the next step would be to feed the same IQ files into a MATLAB program, which will actually do a mathematical comparison. It'll do a correlation function. Now, that correlation function simply is going to take the two waveforms and try to match them up. And how it does that is it actually will take signal and phase information. In this case, it's phase difference for FM. It'll take phase difference information point to point and compare them and see if they correspond. If they don't, it jumps everything over one cycle. In other words, it creates a delay. We call that tau. A delay, and runs the function again and continues to do that. And then it comes back and looks at all of the comparisons it made. When it made at the exact time, when it made maybe a microsecond later, 2 microseconds later, and whichever one has the highest score, that shows you that you've now correlated, and they can tell basically from the time difference what the difference in distance, physical distance would be, because radio waves traveling at 300 million meters a second. All right, so let's go to MATLAB and take a look at that. Okay, so here's the MATLAB program all loaded up and ready to go with this correlation magic. So I'm going to run it. And it's taking in both files. It's going to do that calculation. And then it'll display some graphics. And it'll generate a map with the points. All right, so on the left-hand side is the reference signal. Actually, it's both of them in blue and in orange. Blue is the first segment, which preceded the weather segment, and then orange is the second segment. Now, on this bottom box on the left, you see that it's actually correlated at 2 different delay times. It correlated the first reference and the second reference at 2 different delay times. That's not really good. You want those to actually kind of match. And it only happened to me once in all of my experimentation. And that could be from either reflections, or the fact that we're using older SDR dongles, and the guy who put this project together basically recommends we use the newer ones. They're a lot more stable. But despite that, it'll try to pick the one that it thinks is most reliable. Now, on the right-hand side is the signal itself. This would be the weather station signal, the middle segment. And again, as you go from top to bottom, they're just zooming in closer and closer. So the left-hand side tries to get you fixed in time, and then the right-hand side tries to calculate the delay based on that, and that's the way they get around not using a disciplined clock. This figure here, the first graph in time here, see it's 3.6 seconds. That's the whole snapshot. And you can see how the digital's first, a lot higher amplitude than the FM station. The FM weather station's in the middle here, and then the digital again. The top was my receiver, the bottom was Pat's receiver. Ultimately, we'll be doing this with 3 pies simultaneously, and that's how we get our cross reference points on the lines. Their intersections, line intersections, to find out where the signal's coming from. Alrighty, so I said that generated a map, and let's see where that map is. This might be it, or an old one, but I'm going to reload it. Okay, so here's the map. I'm going to zoom out, and I have a few points on this map, but the pertinent ones for this particular run are these. This one up here, you can see it says receiver 2. That's mine at Port Jeff Station. The one down here is Pat's. Okay, this is the Selden transmitter. We're not using that in this experiment, but I just have that as a mark there. We have 2 digital TV stations here. One is at around 527 megahertz midband, and the other is 563. We're using the 563, but actually I found out if I go up towards the top end of that 6 megacycle bandwidth, I think there's some audio signal up there which is good to track on. So I'm actually listening on this experiment at 565,750. And all the way over here is our target. And this is the National Weather Service transmitter. We got all these latitude and longitudes, off the internet. But this one particularly, Pat helped me out because he had a friend who actually worked on the site. So he verified the location very well. So you can see the line. Not too bad. Now, I want to tell you, we're not there yet. These, I have many more misses than hits. And again, I think we're going to try out the new dongles, the SDR dongles, and hopefully that'll help a lot. I'm going to experiment with a lot of the variables in the program, but this run was okay. And I'm going to zoom in a little bit more. And basically, I guess we're on the wrong side of the road. Well, yeah. So he's over here, and we're, I don't know how far that is, but this is where we would be. Now, presumably, if you had some other tiles, you'd get another line and another line, and we get a point of intersection. However, I only have these transmitters to work with. I really don't have many choices, so I had to pick what was available. And the fact that the 2 receivers are here, and this guy's way out here, is probably not typical of the operation. In other words, I think we'd be operating in a more contained area. And if you have three receivers, your best resolution is if it's within the boundaries of those three receivers. Um, the way these hyperbolas work is they're kind of accurate within, but as you the time delay is not equivalent to the distance delay, as it were. You'll see that in some of the notes. I had mailed out some notes from the designer. But anyway, there you go. And we'll keep punching away here. I think we're on to something, hopefully. And, it's cheap and dirty, and it seems to work pretty well at some time. So we're trying to hone it down. Again, we're not there yet. I don't have the consistency yet that I need, but there are probably reasons for that, and I think we'll get there. So with that, stay tuned. Thank you.